was a couple of points missed out on the opening ceremony, so I'll just have to cover those now. Having mentioned that PLANCKS is the largest one this year, we actually have a map put together covering all the participating countries just to demonstrate the global scale of PLANCKS and how it's impacted this global physics community and brought people together here in Trinity and into this exact room between all of you. So this really highlights that we've covered a lot of Europe and gone all the way into different continents to bring everyone here to compete in the competition, but also to learn from different speakers, to be educated together, to share ideas, share knowledge, and all come out with a better perspective on physics, on the global scale, and the challenges that you might come across as physics students, but also aspiring physics researchers. And then also with the decade of PLANCKS that was mentioned yesterday, for those of you that was in the student talks, here's the list of locations of where PLANCKS has been held. So right now it is restricted to Europe, but with the growing scale of PLANCKS, who knows where we'll end up in the future. Maybe if it's going long enough, we'll cover the entire world map. So with that, and all of that covered, a nice bit of perspective to show you what you really are a part of by being here and participating in PLANCKS, I would like to introduce our next guest lecturer, Professor Sinead Ryan, who is the Dean of Research here in Trinity and was the head of School of Maths and also the Theoretical Physics course director, and has done a lot for Ireland joining CERN as well. So I'd like to welcome Sinead.
Super, thank you very much. Do we have a clicker? No, okay. So, thanks. First of all, thanks to Connor and colleagues for the invitation to come along and talk to you today. So I'm going to talk to you a little bit, we're going to do some physics. Now, I realized as I was just looking at this front row here, I didn't get one of these blue t-shirts, but I did still somehow manage to come in the right color, so that's, I suppose, good. Okay, so I'm going to tell you a little bit about particle physics. I'm a theoretical particle physicist, so this will be very much from the sort of QCD is quantum chromodynamics, and I will tell you a little bit about what that is as well. And this will be from a sort of more theory perspective, I suppose, in this talk. What's happening at CERN, what's happening in particle physics, where are some challenges and open questions. And I know that you'll hear more tomorrow from Clara, more probably on the experimental side, so you'll have the two sides covered between us both. Okay. All right. Okay. Okay. So let's have a look then. So here we are. So this is the history of the universe. Now, particle physicists are almost never accused of lacking ambition. So what we would like to be able to do is to explain the universe from the Big Bang, or very shortly afterwards, through its evolution and all of the different stages over the more than 14 billion years to where we are today, which is over there on that right-hand side as you're looking at the plot somewhere. So we go through a phase of very rapid expansion just after the Big Bang, where the universe is essentially some sort of fireball, so it's a very hot, dense soup of stuff. And then as it expands, it cools, and as that happens, slowly matter starts to form, or basic fundamental building blocks of matter start to coalesce into things like protons and neutrons, and galaxies start to form. And then finally, here we are today, when we look out at the universe from telescopes or out our bedroom window or what have you. And so this is the sort of picture that we have in mind to try to understand where we are and how we've evolved from that moment of the Big Bang. There are some numbers down there to give you a scale in time, but also a scale in energy. And you can see that the universe was extraordinarily energetic in that early phase where it was hot and dense, and then as it expands and cools, of course, that energy dissipates. But if you think about, so from that previous picture, here's what we know about the universe, about the matter content, or the content of the universe today. And so you can see that there's, there are just three things to talk about on this pie chart. So one is the 4.6%, which is the matter, visible matter, that makes up all of the stuff that we see around us. Do I move too much? Is that the problem? Yeah. Sorry, I'll stay here. So, visible matter. Everything here, when you look out, you see the stars, you see everything. That's the visible matter in the universe. That's 4.6% of the content of the universe only. The rest has various descriptions. So we have a chunk of stuff which is called the dark matter. About 24 to 25% of the universe is made up of dark matter. And the more sinister titled dark energy is roughly 71, 72% of the content of the universe. And of those two pieces, the two dark sectors, dark matter and dark energy, we really know very little at all. So dark matter, we have some hints about at least what it might be. We know that it doesn't interact very much with visible matter or at all. It interacts only weakly. And it's dark because it's not visible to us as we look out to the universe. So we infer its presence from observation. So for example, from looking at light bending around galaxies and the rotation curve of galaxies. And dark energy, we really don't understand at all. So what we know is about 4.6% of the universe. So this is the visible matter around us. So that's either, I suppose, you can think about them, you can be the optimist or the pessimist in the room, and you can say that knowing 4.6% about something is fantastic because it's a huge challenge, or it's very depressing because we spent a long time and we've learned something about almost 5%, but there's a huge amount that we don't know. And why don't we know that? So I'm going to focus, though, on that 4.6%, for the obvious reasons that we have some handle on what's going on in there, and we have some really very beautiful theories that explain what's happening, or how the matter in our universe, the visible matter in our universe, interacts. So to set the scale for that, here's a picture for the sorts of distance scales that we're talking about, just to orient ourselves. So you can think about, we all know how matter is made up from atoms. They're about 10 to the minus 8 centimeters across. Sort of roughly speaking, a length scale for an atom. But of course, inside the atom, you have a nucleus with electrons whizzing around it, but the nucleus itself is about a length scale of about 10 to the minus 12 centimeters. And you think, okay, at some point we thought that was fundamental, but it turns out, as we now know, that that's not fundamental. What that means is it's made up of smaller things. And so we know, of course, the nucleus is made up of neutrons and protons. And there we're, again, getting into even smaller scales. And now we know that the proton and the neutron itself, those objects, are not fundamental either. And they have fundamental constituents of matter called quarks. And those length scales are about 10 to the minus 16 centimeters. So as a theorist, what we would like to do, or what we try to do, is to understand nature, matter that we observe around us in terms of those fundamental building blocks. And to our best understanding today, those fundamental building blocks are quarks with a length scale of about 10 to it's about minus 16 centimeters or so. So that's the scale at which we're building theories and trying to understand matter. So how well do we do? Well, we want to understand this matter in terms of these fundamental building blocks, of these quarks, but in terms then of the fundamental forces through which these elementary particles interact. And again, as we understand it, there are 4 fundamental forces, and I'm sure you've seen these before, you know these names already. So we have electricity and magnetism, the electromagnetic force, the weak nuclear force, and the strong nuclear force. These are the 3 pieces of my jigsaw puzzle that fit nicely together, and I'll say a little bit more about that in the next slide. And then, of course, the 4th fundamental force is gravity. And gravity doesn't quite yet fit into this nice, coherent jigsaw puzzle that we have almost completed with 3 out of the 4 fundamental forces. So we have a theory, in fact, that allows us to explain in a coherent way those 3 pieces of the jigsaw puzzle together. And gravity sort of sits out there on its own. So why does gravity sit out there on its own? Well, if you think about the interaction scales, the length scales that are involved in these nuclear and the electromagnetic force, they're quite short range, so the weak and the strong nuclear force. These are forces that act on the nucleus, the elementary, the sort of small building blocks of matter. But gravity, as we know, acts at extraordinarily great length scales. It's very weak, and it interacts with matter in a very particular way. So gravity is quite a different beast, if you like, to all of these, where we have a quantum mechanical interpretation for 3 out of the 4, but not for gravity. So what I'm going to focus on then is the 3 that you see here. There are, of course, I mean, when you think about how to bring these 4 things, these 4 fundamental forces together, there are also, of course, there's a lot of theoretical work in the direction of string theory, which thinks about how to bring these 4 together in a very beautiful, very mathematically rigorous, and very satisfying way. But I'm going to focus on the standard model, which is a very boring name for what is a really beautiful and a hugely successful theory, which is the unification, if you like, of 3 of those 4 fundamental forces. So over here, I'm just reminding you of the jigsaw puzzle pieces. In fact, electricity, magnetism, and the weak nuclear force were unified or described in a single, in one theory called the electroweak theory, and which received a Nobel Prize in 1979. And the strong nuclear force was also led to the Nobel Prize, so it was first discovered or written down in the early 70s, in 1973, I think, by Gross, Pollicher, and Wilczek, and then they were awarded a Nobel Prize in 2004 for their work on the strong interaction. Together, these 3 of the 4 fundamental forces are described by this standard model, as I've already said. And here you have a picture on the right-hand side of the elementary particles that interact under these 3 fundamental forces in the standard model. So I've mentioned some of them already, but maybe let me just quickly say a few things about what's going on here. So the purple ones are the quarks. So the quarks are the building blocks of matter. They're deep inside the proton. We saw that in some previous picture. There are 6 quarks that we know of. They have quite nice names, rather whimsical names, like up, down, strange, charm, top, and then depending on who you ask, it's either beauty or bottom. And these quarks, these 6 quarks, then they interact under the strong nuclear force, and they do that by exchanging a force particle, which is called a gluon. And similarly, as you know, we have electrons, for example, which interact under the electromagnetic force, and they interact by exchanging photons. But we also have leptons, and here we have now the weak nuclear interaction coming in through through electron neutrinos, a muon neutrino and a tau neutrino. So we have a set of these fundamental particles, and the other particles, so-called force carriers, move the force or carry the force between the fundamental particles. So they can be gluons for the strong interaction, W and Z bosons for the weak nuclear interaction, and the photon for electromagnetism. And then we have the Higgs. This was the Higgs boson discovery. This was the final piece of the standard model puzzle, and that, as you know, has also now been discovered and sort of finishes the picture of the standard model in a very, very beautiful way. So the standard model is embarrassingly successful. So why is it embarrassing? Well, it has withstood every experimental test that we have thrown at it, and it has met every challenge in the sense that no crack has been found in the standard model, no deviation from experimental measurements has been found. Theory and experiment agree very beautifully under these 3 out of the 4 fundamental forces. But we know in our heart of hearts that it's not actually the full description of the world around us because of that jigsaw puzzle that I told you about earlier. It doesn't describe gravity, but it also doesn't give us any explanation for why we live, for example, in a matter-dominated universe. There is no explanation in there for the asymmetry that we see. The reason that we're all here is because we live in a matter-dominated universe, and there is an asymmetry between the amount of matter and antimatter in the universe. This is not explained by the standard model. It obviously also does not tell us anything about dark matter, otherwise it wouldn't be dark. I would be able to tell you something about it. As I said, it doesn't describe gravity, and it doesn't really give a satisfactory explanation for why why this arrangement of fundamental particles is here. We call them 3 generations, so there are 3 generations. In each generation there are 2 quarks, so you can see the generations given there by the Roman numerals on top, so up and down, charm and strange, top and bottom. Why are there 3? Nobody knows. We don't understand whether the quarks and leptons and the standard model doesn't give us a satisfactory solution for whether they're really fundamental. It looks like they are so far, and all experimental tests imply that they are, but we don't have a theoretical grounding for that statement. So a lot of unanswered questions about this standard model. And as we go then to test this, we look for something that is beyond that standard model. So the place, at least today, where most of those tests on the experimental side are carried out is at CERN, at the LHC, the Large Hadron Collider, which really is the world's largest experiment, or the biggest machine operating on the planet today. And it's an astonishing feat of engineering and human ingenuity and complexity. On the Swiss-French border, the 21 member states is probably a little bit out of date already because new states are joining all the time. It's about 100 meters, the ring is about 100 meters below ground. You can see, many of you will know already, you can see here it's beautifully situated on the Swiss-French border. Geneva's over there somewhere. You can see the lake in the background, see the mountains behind. It's very easy to go skiing if you're at CERN. It's very nice. You can go to the lake as well in the summertime. Lots of nice things to be said about CERN. But most impressively, you have this fantastic experiment, which is 27 kilometers around. It works by moving beam lines, so bunches of particles around this beam and colliding them at 4 points. Those are the names then of the detectors, so ALICE, ATLAS, LHCb, and CMS. Those are the 4 points at which the beams collide, and measurements are taken. To bend the beam around that 27 kilometers, you need supercooled, superconducting magnets, which are operating at a temperature of about minus 273 degrees Kelvin, just above that. So colder than space. And they're held at that temperature. So already that's a sort of an astonishing thing to be able to do, right? An engineering accomplishment. And you get about 1 billion collisions per second when the machines run. Colliding particles at close to the speed of light. So here at this astonishing facility, the standard model is put to the test. Everything that we know about particle physics is tested here. And what we're looking for are chinks in the armor. We're looking for cracks. Where is the new physics that we expect to see? Why? We know the standard model is not complete, so we look for the next step or the next piece of the puzzle. And that's happening from the experimental side here at the LHC. But it also, from the theoretical side, and this is where I'm going to zoom a little bit now in on one in particular fundamental force, and that's the strong force. So on the theory side, even within the standard model, you can do an enormous amount of theoretical work to understand how these interactions work, to make predictions that help to test then the standard model and predictions for where the new physics might be beyond that standard model. So I'm going to tell you a little bit about the strong force, or quantum chromodynamics, or the secret life of protons, if you like, because QCD, or quantum chromodynamics, is the quantum theory of the strong nuclear interaction. So it tells us, it's a mathematical theory for how the quarks and gluons interact. So just some interesting pieces of information, maybe, about this. So it is still the only known, experimentally realized, non-abelian quantum field theory. I'll tell you a little bit on the next slide what I mean by quantum field theory. Some people might know a little bit about quantum field theory, others might not, so I'll say a little bit about that in the next slide. But it's a deeply weird theory in many ways, and I'll say a little bit about that in the next couple of slides. And it gives us a place to explore these non-abelian, strongly interacting theories where we have actual experimental data. So as a theorist, you can play, like it's like a sandbox, you can explore properties of theories that have these sort of strongly interacting behavior, and then see if it actually is borne out by reality by testing your predictions against experiment. And importantly, when this predictions and theoretical input from the strong interaction physics is crucial for understanding, making predictions about physics beyond the standard model, finding those chinks in the armor of the standard model, breaking it apart and trying to understand where the new physics might be. Okay, so a little bit on quantum field theory. Now, there was a little movie in there, which is not working, but we won't worry about it. A quantum field theory is just the framework, so it's a mathematically rigorous framework that describes the quantum mechanical behavior of particles. And so in the field theory, we consider these subatomic particles as fields, which are continuous through space, and the most familiar example of that is an electromagnetic field. And then you can think about ripples in this field, almost like dropping a stone. The usual analogy is dropping a stone into a lake, and you see ripples that form, or those waves, have a quantum mechanical interpretation then as particles, so for example, as photons sticking to the electromagnetic analogy. And there's a similar setup, if you like, for all fundamental particles. So we have field theories. You can think about quarks, gluons, and Higgs as fields in this sort of quantum field theory setup. So why is it difficult, or why is it tricky? Why do you not actually get to quantum field theory until fourth year of undergraduate, or maybe masters of undergraduate, after undergraduate? And it's complicated mathematically because the theory has to describe many particles and their interactions. So anything that interacts under the strong interaction, all those quarks, you have to describe all of that in one theory. And also, there's a statement here that the vacuum is not static, and what that really means is that in the background, you have quantum mechanically allowed creation and annihilation of particles. So constantly happening. So the vacuum, so-called, makes it sound like it's a very static thing, but actually what's happening inside a proton all the time is the creation and annihilation of states, of particles, quarks. And the quantum field theory has to describe and cope with all of that, and then allow you to make predictions with that theory. So it's a highly dynamic theory. Okay, but you can write it down. Okay, so here's QCD, and in fact, it's even simpler than it might appear. So it's just the top line of that blackboard. That's QCD. So it's the quantum theory of the strong interaction. It has two terms. And there's some definitions underneath, right? So if you've done some classical field theory, for example, some of this might look a little bit familiar. The first term is just, the G's there are just field strength tensors, so you just have a G mu nu, so it's like classical field theory, so classical electrodynamics even. It's a similar sort of thing. And the definition of that field strength tensor is given there on the second line. And also the derivative term, which is this D, the capital D there, is just a fancy derivative, which we don't have to worry about. And that's it. Okay. So why did they get a Nobel Prize? Well, you can say it doesn't look too bad. It actually, as I've said already, looks a little bit like QED, quantum electrodynamics. And here, for quantum electrodynamics, we know what we're doing, right? We have a fantastic theoretical control of QED. We can make calculations to extraordinary, ridiculous levels of precision that have all been verified by experiment. So what's going on here then? Well, if I take my blackboard again and just zoom in on one term in that definition, so that field strength tensor piece, you see there's a regular d mu a nu piece. And then there's this second term here, which is a mu a nu. So the A's there are the gluon fields, essentially, let's just say. And what this second term tells you is that those gluons, the force carriers, are interacting with themselves, with each other. So this is very different from electrodynamics. photons don't interact. Gluons do interact. And so you get Feynman diagrams where gluons can interact with each other. And they exchange color, which is just a word we've given to a quantum mechanical property like charge. But they interact with each other without any quarks in sight. And that makes the theory very different from QED. And it also gives rise to weird and wonderful possibilities. So baryons are just combinations of 3 quarks inside, like a proton or a neutron. A meson is something like a pion, so it has a quark and an antiquark inside in it, so pions, that's okay. But we can also have glue balls, and glue balls are just gluons interacting together. There are no matter particles in there, there are no quarks in there, but this is a visible, or in principle visible state of matter, allowed by QCD because the gluons interact with each other. All from that one term. So, there's a lesson in there somewhere about, looking after terms, or taking care of terms in various definitions that you might want to carry forward to tomorrow, I don't know. Anyway, QCD lets you do then weird and wonderful things. You can make baryons and mesons, nice normal things like protons and pions, but you can also make, as I've already said, weird things like glue balls. So that's a bound state of matter that is, you can search for it in experiments, and actually, so everything, I should say maybe on this bottom line here, is allowed by QCD in theory, but has not been discovered, well, some of them have more recently, tetraquarks have, by experiments in practice. The glue ball, there was a talk this week at CERN from an experiment in China where they have now the most convincing evidence for a glue ball that has been seen so far in any experiment. And actually, a large part of how they identify that they've actually found this glue ball is by comparing it to theoretical calculations using a method I'll show you in a little while. Okay, so there's a whole spectrum of things you can do that are peculiar, that go far beyond the sort of normal proton that we're all used to. And in principle, you want to be able to, with that Lagrangian that I showed you on the previous page, calculate, predict the masses of all of these, and the other properties, decay properties, interaction properties of all of these sorts of states. Okay, so maybe I thought I would just say just a couple of words. This is quite a busy slide, so I'm just going to summarize it very briefly and say that QCD is, it is a theory that is astonishingly rich in, for example, in symmetries. It has a large number of symmetries, including SU3 color symmetries, U1 symmetries. It has a color symmetry, I've already said, sorry, it has a chiral symmetry, which applies as you go to very light quark masses. It has symmetries under baryon number and axial charge. It has scale invariance. It has CP and T invariance symmetries. It's a beautifully rich theory with all of these symmetries. Of course, you have to accommodate all of that in the calculations that you do as well. And it is responsible for the mass of visible matter. And it is not that the Higgs boson, for example, gives mass to the visible matter that we see around us. We have, through QCD, dynamical mass generation, through those interactions that I showed you on the previous slide where the gluons are interacting with themselves as well as with quarks. So here's Peter Higgs, but the Higgs boson is not the reason for the mass of the proton. So you can think about what's inside in a proton. So a proton has 3 quarks in it, so 2 up quarks and a down quark. In some units that don't matter, the masses of those things are approximately 2, 5. So we've got 2 up quarks and a down quark. If you add up the masses, forget about the units. I didn't say that, sorry. In some units, you end up with a number which is about 10. But the mass of the proton, which is made from those 3 things, is 938 in the same units. So only about 1% of the proton's mass comes from the constituent matter particles inside in it. So where's the rest of the mass coming from? The rest of the mass is coming from the energy of the interaction between those quarks in the proton. So very simple, boil it down to E equals mc squared, and the strength of the QCD interaction, so the strength of the strong interaction that holds the quarks together, so they interact with each other, right? The strength of that interaction is enough to give the mass of the proton at the level of 900 or so in some units, when the constituent particles are only 10 in the same units. What's happening here? So QCD is very weird theory. So as you start with two quarks like this, and you pull them apart. Now, in any normal theory that we're used to, as you pull apart things, the interaction between them gets weaker, right? Because you increase the distance, and the strength of the interaction falls off with the distance. In QCD, that doesn't happen. The interaction strength grows linearly with distance. So you can think about it having an elastic band and pulling it apart. As you pull it apart, there's more and more energy stored in that string that is holding the two things together. And that energy then translates into mass for the proton. And all of that is built into that Lagrangian, which only had two terms that I showed you a couple of slides ago. Okay, so there's a lot of words in here which are important, but we won't worry too much about them. But I'll say one sentence about each of the things here. So confinement. Confinement is the fact that the string, if you like, the interaction between two quarks gets stronger and stronger as you pull them apart. So it means that you never see quarks floating around in nature. They're confined because the string, the energy, keeps them together. Asymptotic freedom is almost the opposite. Asymptotic freedom is when you look deep inside the proton, so where the distance between the quarks is very small, they hardly have any interaction at all, and they're free in that asymptotic limit where the distance between them goes to zero. So at confinement and then asymptotic freedom. And to get from one to the other, we have something called a running coupling. So the running coupling is just a way of discussing or describing what happens to the interaction as you go from, and this is what's shown on the plot here. So this is usually what you see when experimentalists and theorists show the plot of how the strength of the interaction or the coupling strength varies with distance. They show something that looks like this. There's lots of points on here. That's the measurement from theory and from experiment, different measurements. You see they all lie along this predicted curve, which is very nice. And you see that, so on the y-axis you have the coupling, so the strength of the interaction. And so basically what this Q here is sort of a proxy for the distance. And so as you go to the inverse distance, so as you go to so as Q gets large, that's low energies. I'm getting the wrong way around. I'm going to flip it around. So this is what you usually see. And then this is the convenient version. Sorry, I'm getting myself confused here now. So this is the convenient version, where all I've done is I've flipped the plot, but it works nicely because I can put distance along the x-axis. It's still the coupling going there. So here's the coupling strength. When the distance between two particles is very small, the coupling is a very small number. If you increase the distance, so you're pulling things apart like this, you're increasing the distance, you see that the coupling grows dramatically. So this tells you something. In particular, it tells you that all the theoretical tools that we developed for QED, for quantum electrodynamics, rely on there being a small number in which I can do a perturbative expansion, like a Taylor series expansion, basically. And that works for QED, but it absolutely does not work for QCD. By the time you're at a point that you're interested in, which might be the radius of a proton, I'd like to know something about the proton. Then I need to do calculations at distance scales of about 0.2 Fermi. At 0.2 Fermi, the coupling is enormous. And that huge number is no longer appropriate for a perturbative expansion or a Taylor expansion. It's not a small number anymore. So perturbation theory, the workhorse of all quantum field theory theoretical calculations until the 1970s, until QCD came along, absolutely doesn't work here. and we have to do something completely different. So what we do that's completely different is non-perturbative, so this is what I work on. We think about the universe in a completely different way, or think about space-time in a completely different way. Essentially, we think about it as a discrete, four-dimensional hypercube for space-time. Still have the same Lagrangian up there, just to remind us that we're still in QCD. And there's some busy words over here, but we just focus on the picture. We just put the quarks on the sides of the lattice. So imagine some lattice in 4 dimensions, which is obviously impossible to draw, so here's a cartoon of what that would look like. You put the quarks on the sides of those lattice, and you make the links that join up the quarks be the gluons. And then you do some maths that makes that all work. And then you solve the QCD path integral. So like Feynman's path integral, but now for QCD, it looks like this. And that tells you everything you want to know from the theory. So I start from the Lagrangian, I make this step where I discretize it, and then I solve the path integral. And this thing here on the bottom is the path integral. And again, some of you might recognize, at least see some familiarity with statistical mechanics. So when you write down how you calculate correlation functions, for example, in the canonical or microcanonical ensembles, you typically write a sort of picture like this, where you have a partition function and then some sort of statistical mechanics interpretation, and this is really what that is. And so this picture then allows you to do numerical simulations. So, in fact, the idea at the beginning, when this was first written down, was not actually to do numerical calculations. It was to find a way to make QCD work in those long distances, where perturbation theory doesn't work. And it turns out that by doing that, you turn it into a theory where numerical simulation works really well. And it turns out, of course, the flip side of that is it turns out that you need extraordinarily large computers to be able to solve that path integral that you saw on the previous page. So you end up doing a lot of stochastic estimation of path integrals. So why do you need a big computer? Well, what you want to do, so you just think about, so in physics, right, the important thing to think about very often are the length scales that are involved in your problem. So think about the length scales that are involved in the previous page. You've taken space-time and you've discretized it, right? So it's just a big 4-dimensional grid. If I want to do numerical simulations, I have to make that a finite system, because obviously I can't do infinite simulations with an infinite size system. So I make it a finite size system, finite but large. So I need to have a system where the box, the overall box that I end up with, is large enough to accommodate the thing I'd like to calculate. Let's go back and think about our proton. So the proton, for example, it has to be big enough that the proton fits into it without feeling the edges of the box, because then you've got some weird numerical interference with the edges of the box, which are not physics, right? The edges of the box aren't physics, because in the real world there is no edge to the box. So I need a big box, but then I also need a very fine grid in the box, because I want to be able to resolve that structure within the proton, so those quarks and the interactions. So I need a big box and lots of very fine mesh. And those two, of course, that then already tells you that I'm going to need a lot of points in this 4-dimensional hypercube. So there's some typical sizes there for you. And the significant problem is, if you multiply out how many points you have in this sort of typical box, and you throw in some additional numbers, 12, which happens to be 3 times 4, which is related to the number of colors and the number of Dirac indices. So there's some physics in the 12. You get to a matrix which is about 10 to the 8th squared. And that path integral that you saw on the previous page requires you to invert that matrix and calculate its determinant and solve this linear system. So M is the big matrix, and you have to invert that to solve, or calculate its determinant to solve that system over there. So hopefully at some point you've all tried to do something like this, probably not with such big matrices, I suppose, but this is a ginormous computational task just to do this. The matrix is large, obviously. It's sparse, which means it has lots of zeros, which means it's ill-conditioned, which means there's a whole world of pain in linear algebra waiting for you when you try to do this. And you also generate an enormous amount of data that you then also have to worry about what you're going to do with it. So you do that, and then you think, okay, right, I managed to do that, that's great. But actually, you're not really done. And the reason that you have to do it thousands and thousands of times is because you're doing a Monte Carlo statistical sampling. So you're doing lots and lots and lots of samples. And then you have to do it all again with a different size box and a different size grid, because you want to make sure that there's no effect of the grid and the box on your physics that you extract. So you do lots of work. And there's a machine that does some of the work. This one actually, I've left it here because it's the most beautiful of the supercomputers, I think. Certainly the most colorful, but it's actually not the fastest anymore. But it's these sorts of machines where the calculations that I told you about on the previous page are being done. And it's also maybe interesting to think about the publicly available resources, compute resources on the planet. About 10% of those are going to lattice QCD calculations at any given time. So it's an enormous calculation challenge, but it's also pushing exascale computing. So to do what we do, you have to do an enormous amount of algorithm development and also architecture, hardware, and software development. So it pushes a lot of development in computing as well. If anybody wants to ask me about where machine learning or quantum computing might be in this whole picture afterwards, I'm happy to talk about that too. Okay, so what can you actually do with this? I've totally lost track of time. So I don't know, when did we start? Okay. Anyway, I'll say some stuff and then I'll stop. Because I know I'm standing between you and your dinner now, which is terrible. Okay, so here's just a blitz of stuff that you can calculate. This is not comprehensive. This is not everything, of course. It's just a snapshot of some things. So there are things. I'm going to say a little bit more about this plot here and this one here in a minute. So let's focus on the sort of the top right side there. Top middle is a calculation of light particles, so baryons made up of light quarks. You see a neutron is there somewhere, so the neutron is there, and it's the electromagnetic splitting. So the mass difference between the neutron and the proton is what's measured there. And in this amazing calculation, they also included not just the simulation of QCD, but QED as well. So the effects of quantum electrodynamics with quantum chromodynamics to work out these calculations. And everything in blue is a prediction from lattice. And then you can see that the prediction is the dot, and the experiment then came along and measured in some cases, and you can see that they line up beautifully. Over here is an example of how the QCD calculations either limit or inform searches for new physics. So this is a very weird way of representing everything we know about the Standard Model. And if the Standard Model is truly correct in some sense, then all of those bands that you see, all those many colored bands there, should meet at a point. And you can see, if you have eagle eyes, you can see there's a triangle drawn in there in black. And if the Standard Model is correct and there's nothing else going on, then all of the bands meet at the apex of that triangle. Now, they sort of do, but that's because they have big error bars. So the width of the band tells you how uncertain the measurement is. And you can see within the uncertainties, it looks like everything's okay. But if I were to shrink those bands down dramatically, then they might not all meet at that apex point. We're not able to say yet whether they do or not. And the reason those bands are there is because uncertainties in the QCD piece of the puzzle are the dominant effect in those bands. So better calculations from lattice QCD will inform this. And then this one down here, I think because it's the most recent little bit of fun that we've had in particle physics on the new anomalous magnetic moment, which you might have heard about, measurements of G minus 2. It's been measured, it was measured first at Brookhaven on Long Island, and it was measured, then the whole experiment was dismantled and shipped by road and sea down the East Coast, up the Mississippi, and finally across to Fermilab, where it was jigged, I think that's the technical term, to make a new measurement of this particular property of the mu1. And the purple line, the purple bar, sorry, is the experimental line, or the experimental measurement. And the green stuff and the red stuff are the theory calculations. If theory and experiment agree, then there's nothing to see here. Standard model is working perfectly. If theory and experiment don't agree, then there's something going on. Something interesting is happening. And it might be new physics. The situation until a couple of years ago was the purple band and these red points. Looked like there was something really interesting happening. That's why they dismantled the experiment, shipped it down the East Coast all the way up to Mississippi and over to Fermilab to rerun the experiment. And then just as they were publishing their new results, the very top point was published from a lattice QCD calculation. And you see that it is in very nice agreement with the experimental number, which essentially is saying there's nothing to see here. And in fact, theory and experiment agree nicely with each other. This has become, obviously, as you can probably imagine, a hot topic in particle physics, to understand who's right and who's wrong here. Somewhere, something's gone wrong. So either theory and experiment don't agree, which is interesting because there's some new physics, hopefully, at play, or theory, green theory at the top and red theory at the bottom don't agree. They're different approaches, different methods. And then, I don't know, maybe if you're a theorist, it's really interesting, because then you have to figure out, like, why don't the two different versions of these calculations agree? So this is something where lattice is really pushing, actually, progress in the field. I'm going to give you two quick topics that are interesting, because they're very much in QCD, but they also tell you what we don't know about QCD, despite the fact that since 1973, we know the Lagrangian. For a long time, we've known the properties of the theory, and for a long time, we've been doing calculations. There's still many things that we don't know about QCD, and one of them is around what we call strong exotic matter. So, it's theory, experiment, and the so-called XYZs, and this is a story that dates from 2003, which I think is not that long ago, but you probably think is ancient history. So here's a picture of what was known in experiment, and it's nicely color-coded, so you don't have to worry too much about what's going on, where everything is. Just look at the yellow stuff. The yellow stuff were states, things that were measured by experiment, established, expected. Nothing to see here. The gray stuff are states which were predicted by theory in a very normal way. We all thought it was perfectly reasonable. These are some predictions, but they hadn't yet been discovered by experiment, but they were bound to be discovered by experiment. Okay, so they're the grey ones scattered around, a little bit higher up. They're higher in energy, so they're harder to find at experiment, which is why they haven't been discovered. And then there's the stuff in whatever colour that is, sort of salmon colour, and the purpley coloured ones. And these just appeared out of nowhere, unexpectedly, at experiments. So the first was in an experiment in China, or Japan. Japan was first, I think, and then China, and then the LHC in Europe. They basically switched on the experiments, and these things popped out. And it was absolutely unexpected. Nobody knew what they were, apart from some hints that we knew what sort of quarks were inside in them, but we've no idea whether they are, to go back to the picture that I showed you early on about the different sorts of things you can make. Are they tetraquarks? Are they molecules? Are they hybrids? No idea. Nobody knows. So this was a very unexpected discovery at experiment in 2003. And now it's 20 years later, and we still don't know, actually, what they are. And that's for theory to figure out. Experiments have really done the work in discovering them and classifying them and figuring out a lot about the quantum numbers. But theory has to figure out what their actual structure is inside. So we do this in calculations in QCD, lattice QCD, and this is one that I was involved in, which is calculating the spectrum, many different energy levels, which you can map onto these guys over here. And what's interesting is that we can calculate what are exotic, manifestly exotic these particles that I showed you on the previous page, or a couple of slides ago, where you have these hybrids and tetraquarks and things like that. We can calculate those in a lattice calculation and then try to understand what's happening over here in experiment. So that's still work that we are only just figuring out how to do. And then you turn up the temperature and you ask, what happens if I look back in time when everything gets warmer and the universe heats up? And here there are just many, many questions for which theory does not have answers. So in particular, this is the phase diagram for QCD. And it's sort of cartoon-like, right? And the reason it's sort of cartoon-like is because we don't actually know anything really substantial about it. So temperature goes on this axis, and this is something called quark chemical potential, but really that's a measure of density. So you can think about, density in terms of the universe. So if I go back in time, the universe gets very hot, and if I go out here, the universe gets very dense. And so as I go sort of back in time towards the Big Bang, then I'm out here in this top right corner where there is a plasma, this hot soup of quarks and gluons, unconfined. But I don't know really very much about this phase diagram. There are some phase transitions in there. We're only just about figuring out whether they're crossovers, first order, second order phase transitions, where the end points of those phase lines are. There's a huge amount that we don't know here. But what we can do is start to explore it with lattice QCD. So this is, I'm just going to say just very quickly what's happening here. Here, what we're doing in this calculation is doing a simulation of a particle at 0 temperature. And you see it has a couple of nice peaks. The first sharp peak is the ground state. The second peak is the first excited state in this sort of hydrogen atom sort of style. And then I heat it up. So what happens when you heat something up? When I heat up as a particle, you imagine that it sort of broadens, it thermally broadens, so it starts to melt, basically, right? So it starts to broaden, the width broadens. And so you see that happening here. The peak shrinks, and the first excited state, which is the heavier one, starts to melt away. And so this tells me the temperature, for example, at which these states melt or deconfine in the plasma. So I can say something about the deconfinement phase transition if I study the behavior of these particles as a function of temperature. So I can do that for these are S waves, but I can do them for P waves and things like that as well. Okay, so I'm going to finish, just say a couple of words. So lots more questions than answers, but there's a huge amount going on in this field. You'll learn a lot also tomorrow on the experimental side, which I haven't said much about at all. We're still trying to figure out the bit of the universe that we can see, knowing that there's a huge amount more to also understand. But there's a very productive, constructive, and very useful synergy between experiment and theory in this business, right? Where we go through phases. Sometimes experiments are finding things, like those XYZs, which theory has to calculate. Sometimes theory is calculating or predicting things, which experiment then has to find. And there's a very nice tension almost between these two that keeps us all on our toes. And obviously this is just a snapshot of what's going on, and there's lots of exciting things happening. And one of the most exciting things that is happening here in Ireland, and the Provost mentioned it in her opening address, is that Ireland is finally joining CERN, so we will actually be part of this. And I would just like to, again, as the Provost mentioned, point to the work by Connor and other colleagues in the Theoretical Physics Student Association here in Trinity for actually helping, making a huge effort in the advocacy for CERN membership. I think without them we wouldn't have got to this point. So I think that's probably enough for me, so thank you. Any questions? Yeah. Hi. Can you explain? how it's possible to find them or how it's possible that they're there? Maybe both. Okay. No, it's an excellent question, yeah. So I'm probably the wrong person to ask that question to, since I'm not an experimentalist. But basically what they do, in the experiments, what they do is they look for signals in the data. So, bumps in energy, basically. They can scan, they collide the beams, they take loads of data. And then they can identify, they have very sophisticated ways of identifying the different particles. And they can identify the different particles by spin, by charge, by looking at the trajectory as they come out of the collision. So there's a very sophisticated procedure for identifying particles. And then they can look at where the energy of these states, what the energy of these states is. They can calculate that as well. And so basically this process, looking for a collision, a decay, where they've got, in this case, it was something called a J-psi, which is made from a charm and an anti-charm quark, decayed into products, and then they find all of the products, and then there's one which doesn't fit in the picture, and that one they can identify as a glue ball. So it's a rather complicated procedure. It's not an easy thing, but basically it's by looking at, in the collision, you make this thing called a J-psi, and then that J-psi decays, and they look at the decay products. And then you have to sort of reverse engineer the whole thing to figure out what's going on. It's really complicated. Yeah, it's a good question. Yeah? This diagram, is it this one? Yes. Yeah. So here in this bottom left corner, so temperature goes this way and density goes this way, essentially, right? So you're heating up the universe if you go along this axis, but you're not making it any denser, if you like. And you're going along here, you're making everything denser, but not heating them up. So neutron stars, for example, as we see them, as we know them today, might sit over here extraordinarily dense, but not superheated up. Not in a very hot universe. They're in our universe today, but they're very dense. And then, so this piece here is called the hadron phase because the conditions allow for hadrons, matter like neutrons and protons, to form because the universe is sort of cold and dilute, so not, so conditions we have today. So that's the hadron phase where matter can form. And then as you heat it up, you start to deconfine, so things start to melt as you heat up. And then as you make things more dense, you create something called a plasma, which is like that early universe physics. But you're right, we don't know very much about the borders of these different phases. And that's something that we try to do in theory, but is really hard to do, actually. For a long time, we didn't even know if this line was concave or convex, for example. Now we think it's this way, but it's really hard to do. So it's still a work in progress, very much. Yeah. No problem. Yeah. Yeah, so yes. So in the limit, in some ADS-CFT limit, you can indeed recover some aspects of QCD. Or at least there's, you can make calculations. I think the most prominent calculations have been of glue ball masses, for example, and look to see how they match on to QCD. But it's not starting from QCD. It's starting from a different sort of theory. But it is interesting if you can map one to the other, because you're thinking about, in the ADS-CFT picture, you're thinking about a very different system at higher energies, typically, for example. And then understanding whether that maps to something that you observe or calculate from first principles is really interesting. But they're quite different. And without the QCD calculation, you don't really have you don't know whether what you're calculating in ADS-CFT limit, for example, might be a glue ball or not, or whether it's even correct. Yeah. Yeah. Yep.
You mentioned quantum computing.
No.
So, would quantum computers have like a significant computational advantage for lattice calculations over classical computers? Or?
I mean, the short answer is we don't know yet. The slightly longer answer is that the place where it might have some advantage is along this density axis. So this, part of the significant problem, and I glossed over this up quite a bit, so when we do the numerical calculations for numerical computation reasons, we have to rotate from a Minkowski metric to a Euclidean metric, just to make the probability, the weights in the path integral look like probabilities, so that all the Monte Carlo stuff works. Okay? By doing that, you lose access to real-time physics and to this finite density sector. So no Monte Carlo calculations work as you go in this direction at finite density. So one suggestion is, and people are thinking about whether a quantum computing approach, reinterpreting the path integral essentially, and solving it in a quantum computing environment might work for this sort of physics along here. It's completely unclear yet. There's some models where people play around and it looks somewhat promising, but actually doing full QCD and this, we're a long way from that, I think. But that's one place that it might actually be really useful.
You show the picture where there are like different results from the same field, and some of them match with the experimental.
Yeah.
My question is like, what are those methods that give different results? Is it like different discretization or different numerical?
I've lost. Yeah. More or less, you've answered your own question beautifully, actually. So this one, I think, is what you're probably this one, is it? Yeah.